Hi, everyone. My name is Dennis Keene here. I'll be hosting most of the webinar along with Mike Marley, both with XD Environmental. We had about 20 people signed up for this or so we'll probably have some folks join in as we go along, but I'll start with the introduction type information and we'll go from there. Just as a heads up, the webinar is being recorded and we'll upload a version of that to YouTube. And we'll send a link for that. So you can have it at your disposal as far as the webinar is concerned. Additionally, we're going to have a couple of sections where we have some question and answers. I think what we'll end up doing is if we have some questions in between kind of the SVE theory section and a couple of case studies we have, we'll answer those there so they're fresher at that point, and then we'll move on to the case studies. So Mike Marley will be doing primarily the theory section, and I'll be doing mostly the case study section. So again, this is soil vapor extraction, state-of-the-art design and operation. Soil vapor extraction is kind of a very mature technology, but even for mature technologies, we find that the overall design and implementation of SVE still has some issues associated with kind of state of the practice versus what's going on with state-of-the-art. So big thing here for us is why would anyone listen to XCD? What do Mike and I have to offer relative to experience in this particular topic? So XTD has been around since 1997. Mike Marley has remediation experience going back into the 1980s. We've been on the forefront of many remedial technologies, almost exclusively associated with remediation. Obviously, SVE being one of them. Mike Marley was one of the first implementers of the technology along with air sparging. We do in-situ oxidation, bioremediation, and a number of other technologies. So that's primarily the reason why we think that we have something to offer relative to developing people's understanding of the practice and implementation of SVE. So I'm going to hand this over to Mike now, and he's going to go through the theory section. And we'll do that. And again, use the little chat icon. It's located towards the upper right-hand side of the Teams window, and you can ask questions in there, and we'll see if we can get to them by the end of the theory section. Take it away, Mike.
Okay, thanks, Dennis. So again, as Dennis mentioned, I'm going to go over some of the, not so much the theory, but sort of what's the highlights. So what's the key differences between the state of the art and state of the practice? And as Dennis mentioned, I've been doing remediation since actually the late 70s into the early 80s, and been focused on that all my career, which is spanning over 40 years now. And I was actually, my master's and doctorate work were in basically soil vapor, air-based technologies like soil vapor extraction or sparging technologies. And something that I noticed, one of the benefits of being in the industry for so long, I've seen almost for every technology that comes across our desk, that the state of the art and the state of the technology start off coexistent at the same level, but very quickly with the industry pressures to be able to provide low cost solutions, we see a divergence. We see that the state of the art, which is basically the science behind all these technologies, and the state of the practice, which becomes more of a rule of thumb, more of like what's the cheaper way to do things, and they start to diverge. And this is almost true of every technology that has been developed and is in operation since the sort of 1980s. And again, it's these pressures that all the consultants are under to basically have a low-cost solution for their clients that's been driving a lot of this sort of shortcuts, doing rule of thumb as opposed to truly science. And it's also very, very evident, even in something as conceptually simple as soil vapor extraction. The one interesting thing about soil vapor extraction versus some of the other technologies is it's hard to see the initial failure with soil vapor extraction. You put a pipe in the ground, you draw a vacuum on it, and you get contaminated vapors coming out of the ground. Therefore, it looks like it's a success. It's the failure of soil vapor extraction typically takes a longer time frame than other technologies to determine that it's really not doing what you really want it to do, and the cost to do it and the time frame to do it can become very elongated and more costly if you're not applying the science and more applying the sort of like rules of thumb. Other technologies like chemical oxidation, as an example, you can see failures right away. It's not dosed correctly, it's not applied correctly, and the failure is very evident. But with solid vapor extraction, it's a little different. So next slide, Dennis. So again, the process is as simplest it could be. Basically, you've got you've got contamination in the unsaturated zone that's distributed, whether it's chlorinated, whether it's petroleum, whatever it is. Basically, it's a volatile organic chemical. All you're trying to do is introduce a media, typically air. It's not always air, but that's the vast majority of time is air. And you're inducing it to flow through the subsurface. In flowing through the subsurface, it basically causes contaminants that are on the soil or in the soil moisture to volatilize into that air that's passing by it and into the towards the extraction point, with the low vacuum point, which is your extraction well, and it's removed from the subsurface for disposal. Now, when I was doing my master's degree work and looking at residual contaminants in column studies, I could see that it only takes an inch or two of movement of the air in close proximity to the contamination to fully saturate the vapors with the contaminant. The issue is basically that the air phase that's moving through the subsurface can only contain a certain amount of contaminants before the number of molecules of contaminants that move off of the soil or soil moisture into the air is equaled by the number of molecules that redeposit back into the soil moisture or into the soil. So it's got this concentration maximum that it can have, which is a function of temperature and vacuum, but typically it's a number X. And so when the air is moving through it, basically it picks up that contamination. Once it's saturated, it moves to the extraction well. So the figure that you're looking at basically exemplifies, the air movement through the subsurface, and it's coming from outside the area of impact, or it's coming from the surface in the area of impact. It's coming from all over the place, depending on the pneumatics of the air movement in the subsurface. But when it passes through, the contaminant is picking us up and bringing it to the extraction well. We put in the clay layer there in this grammatic because basically, obviously, the air is not flowing through the clay significantly relative to the more permeable media. So you have a diffusion element, and that's a factor that needs to be considered. Different permeability media need to be considered as well because of the different airflow velocities that occur through it. Contaminant on top of the capillary fringe, also very important. The most efficient air vapor extraction system I ever worked with was basically one in a fractured bedrock, where the air was forced to be in intimate contact with in that particular case, it was xylene, and it was forced to be in intimate contact with it to the point that the air was always saturated with the xylene, and it cleaned up very efficiently. So we're gonna talk a little more about this in terms of the state of the art, state of the practice. So that's the process, and we'll talk about some of the pre-questions that people asked about, how do you know when to shut down and stuff. But go to the next slide, Dennis. It's the design that really is the differentiator between the state of the art and state of the practice. Even the pilot testing looks fairly similar, but it's really the design aspect of it. So the state of the practice, and this developed because a good friend of mine, Paul Johnson, Johnson-Ittinger model, back in the early 80s, developed a one-dimensional model looking at vacuum propagation from an extraction well. And for some reason, the industry took that as a sophisticated design tool, and that's not what Paul meant. And what happens in the state of the art is people, go out there, they install a well, they propagate a vacuum from the well, and the vacuum propagates out into the subsurface, and they measure the vacuum propagation. And 90+% of the time that vacuum propagation is then used in the design process to say, well, I have a vacuum of X, I'm going to use that and I'm going to space my wells accordingly. An example of that, which we were asked to review because it was a failed soil vapor extraction system, was a site in California, which is a 4 to 5 acre site. It was designed based on the state of the practice of looking at vacuum propagation, and it was operating from 2002. In 2018, they asked us to take a look at it because what had happened was basically it was typical interbedded sands. There was some clays, mainly silty sands. They had a high vacuum system operating. If you put a piezometer anywhere in the 4 to 5 acres, you would have got multiple inches of water vacuum. So vacuum was not a limiting factor. It was all over the place. But they'd only removed about 10,000 pounds or a little over 10,000 pounds since 2002. And more recently, in the last few years, only about a few hundred pounds. And when they looked at the soil data, there was still a large VOC mass remaining. And the issue was basically they weren't getting the airflow through the subsurface necessary to volatilize and remove it. The state of the art looks at actually conceptually simple. It's basically looking at you need a certain volume of clean air to move through the contaminated zone and to allow that contaminant to volatilize into it, to remove it from the subsurface to be treated. That's really the major difference. Is vacuum by itself is not a good indicator of how soil vapor extraction will work and how it can be designed to be efficient. Looking at pore gases or clean air coming in and forcing clean air to come into the system to remove the contaminants and saturate that gas volume and be removed is really what it's at. Dennis is going to go over this in this example in a little more detail. This is a site in Illinois that we designed and implemented. It was about 3 acres. It was basically based on pore volumes, pore gas velocities. And within a couple of years, basically, it met the goal. It actually removed about 500,000 pounds of benzene from the subsurface in that 2.5 years and was approved for closure. That's sort of the major difference between the state of the art and state of the design or state of the practice. Next slide, Dennis. So again, as I mentioned earlier, when you go out and you do pilot testing, and most pilot tests look very similar, you've got a well or a series of wells that you apply a vacuum to, and you monitor the vacuum at that well. Some people add vapor probes, which is required and should be done. Some use vapor probes in a number of directions to find out about radial symmetry. Some add them at different depths, and we'll talk about how that design of that pilot test can be very useful to determine not only vacuum propagation, which again by itself is not adequate to come up with a state-of-the-art design, but it can be used to determine permeabilities. It can be used to look at 3-dimensional permeabilities. It can be used to look at anisotropy. It can be used to look at low flows and low permeability material. A lot of information can be gleaned from a pilot test that the state of the art and the state of the practice looks similar, but the interpretation of the data can be very different. The trouble is, again, as I mentioned, in the state of the practice, people are looking at vacuum propagation, and then they're designing a system based on some arbitrary number. They'll say, okay, I've got 1/10 of an inch of water or 1/2 an inch of water or 100th inch of water. That gives me an effective radius of influence. And basically, if I put my wells at that sort of spacing, I should be effective. And that's very typical. And 90+% of systems are designed that well. The trouble is, just because there's a vacuum there, it doesn't mean that you're getting adequate clean air pore volumes moving through the system to get to your remedial goal in the cost and the time frame that you would ideally be looking for. So that's sort of like the point. State of the practice, vacuum propagation by itself is not adequate. Next slide. So as I mentioned, what we're really looking for is we're looking for to be able to understand the clean air, whether it's coming from the surface or whether it's coming radially from an area outside of the impacted zone. You want that clean air to be coming through your system, picking up the contaminants and removing them from the system. That's really going to tell you how your system's going to behave. Pore volume exchanges are difficult mathematically to capture or understand. So in a lot of cases, Dominic DiGiulio, who's the EPA lead in soil vapor extraction, he's retired in the last few years, but we worked with him over the years many times on many sites to help them with SVE closure criteria and a number of things. But pore velocities are a little better or easier to understand and mathematically derive than pore volume exchanges, but it is really the pore volume exchanges that's causing the success with the soil vapor extraction. But pore volume velocities, which give you an indication of the air movement through the subsurface as opposed to vacuum, which doesn't by itself, can give you some sense of this treatment. Dominic had recommended 0.01 to 0.001 centimeters per second velocities. What we have found over the years is basically, those numbers are adequate under certain conditions. Sometimes you need to go a little faster. Sometimes you can get a little slower if it's diffusion limited. When we look at pore volume exchanges, what we have found over the years is, in the vicinity of about 1 to 2,000 pore volumes per year, basically in a sort of like a typical volatile organic chemical spill, typically gets you down to where you're trying to go to. And that's really what we're talking about as a difference. So pore gas velocities is really what you really want to understand, are those pore volume exchanges. Next slide, Dennis. So one of the things in a single well system where you've got a small system where you've got 2 or 3 wells, it's not as big a deal with regard to forming a lot of stagnant or dead zones, which means basically, again, you can have a stagnant zone where basically air is not really moving, yet you can have a significant vacuum detected at that area. It's really that vacuum gradient driven by in cooperation with the permeability of the media that determines your air velocities. So you can have a lot of stagnant air, especially when you get into multiple larger system where you've got multiple extraction wells, because they're, especially if you've got a tight surface. So say you had a paving without any understone or a clay layer above your target treatment area, the air it's very difficult for the air to get in. So it has to come horizontally from distance. And you see that with regard to higher vacuums at the well, more reach with a vacuum. So again, the misinterpretation of that would be, oh, I've got vacuum. I've seen vacuum out at 100 feet. I can put my wells 100 feet on center or 100 feet radius of influence. The vacuum propagation, again, in a multiple well system where you're competing for the same airflow, you'll get vacuum, but you're not going to necessarily get much more air movement. You can overcome this by introducing air to the system. You can overcome this by changing the operation of the wells, not operating them all together. You can change this by a number of different wells. But if you're conceptually thinking about it, you just want to basically be continuing to allow clean air to come into your system, and that's where you're going to be effective. Dennis? As I mentioned previously, basically, even the state of the practice and the state of the art look very similar in terms of the pilot testing. Again, the difference is basically, the bigger difference is the number of points that you have and what you do with the data. So a typical system, as you've probably seen, involves a single well or a multiple set of wells with typically a number of vapor points that are installed in the vicinity at different distances from the extraction well. And typically you want to do them at different radial distances just to make sure you don't have a preferred flow path and you've got dead zones. Sometimes you're applying SVE close to a foundation, and that foundation is deep relative to the vado zone. You might have a stagnant zone near that wall because air can't flow. It's got a sealed surface, it's got a sealed horizontal barrier. So you want vapor probes, you want to use common sense and put vapor probes where you would like them to be to determine where you might have dead zones. Stratigraphy obviously is very important. If you've got a low permeability as well as high permeability and you want to see what's going on in the low permeability, you're going to need to have a well that's screened specifically in the low permeability and one that's specifically in the high permeability. And so layered stratified systems, again, using common sense, you want to understand those permeabilities, you want to get a value for them, and you want to understand the airflow that's occurring in them. So you want to get vacuum as well as permeabilities. Surface covers in some cases, and one example we're going to, Dennis is going to give you, is an open field where they had a vapor issue that was contaminating from the vapor zone into the underlying groundwater above regulatory criteria, but it was an open surface and contamination was near the surface and it was an open field. It was beneficial to add a low permeability cover over that surface to allow you to have less wells and basically better propagation, better airflow through the system laterally, as opposed to just coming in right close to the well that was screened very close to the surface. So again, think of strategy, think of common sense sort of things, like you want to be thinking, how is that air moving through the subsurface? Am I getting clean air coming into my target zone? We should also limit the screen length, basically, because again, if you have a large vero zone, even if it's all nice coastal sand and you have 25 feet of unsaturated zone, if you put a well that's screened from 5 feet to 25 feet, you're going to get an averaging. You're not really going to get a good understanding of the airflow. So it's better to have, you know, a shallow well and a deeper well, and then look at the vacuum propagation through that and sort of see, you can again tell not only permeabilities, which might be very similar, but the vacuum vapor probe readings are going to give you a lot of good information on anisotropy and basically where the air is coming from to feed the system and where you're getting the cleaner pore volumes coming from. Again, this is the multi-level in different directions. Next, and Dennis is going to go through some case studies in a little more detail. So again, don't be put off by mathematical solutions. They're basically, all we're doing is we're using a tool. Some of them are very simple analytical solutions, some of them more complex solutions that are 3D. It depends on the system you need to use, but these are very easy to use models that basically take that data from the permeabilities or from the extraction well that you use, the permeabilities, the flows that you measure, and the vapor probe data, and you can basically, you're doing a fitting of the data to the model to tell you what the permeability is, and also tell you basically something about the anisotropy, something about the directional preferences, additional data about where the air is coming from, what the velocities are, so that you can design your systems. The little drawing at the bottom basically is showing these velocity vectors, and we use the criteria of the 0.01 centimeters per second. Anything that basically is white surrounding that is not meeting that criteria. The red little vectors you're seeing are meeting or exceeding that criteria. So you can see from that that the target area, which is the organic shape, is pretty well covered by the well layout that was provided for that particular site. So if you go to the next one. So I'm just going to do the pellet test layout, and then I'm going to switch over to Dennis. So again, this is a small site. This is the one that I mentioned earlier, and Dennis is going to go to it in more detail. We choose a larger site, we choose a smaller site. This was the one that I mentioned earlier, which is at an industrial facility where there was still impacts in the vero zone, but they were sufficient. This was chlorinated solvents. They were sufficient that the vapors that were formed in the unsaturated zone, there was not saturated contamination directly from DNAPL or anything. It was the contaminants in the vero zone were basically creating vapors. Those vapors were denser than air, and they were moving down into the groundwater, and they were sufficient to basically cause the groundwater to exceed criteria. A lot of times, if you look at data on sites and you basically see contamination up or contaminated groundwater up gradient of where the contamination is in the soil, a lot of times it's just through vapor migration and redeposition into the groundwater. So here's a simple system. You got a single SVE well, and you've got multiple vapor probes. You can see VP stands for vapor probe. You've got shallow, intermediate, and deep. You've got basically the SVE well, again, shallow and deep, because we did have a stratified system here. We had more permeable sands up above and below, and then a little less permeable layer, which is where most of the contamination resided. So you can see that this was a simple system. We just were able to go forward with this and basically do the testing and come up with the design. So the next slide, and then again, we'll switch it to Dennis. So this is the 3-acre site that we cleaned up. This is again a much more complex site. It was 3 acres. It basically needed a more significant extraction system. It was a stratified system, which Dennis will go over. We knew that there was going to be, because the lower layer that was a target area was beneath a semi-continuous clay zone. We knew that air was going to find difficulty of getting, and therefore to get those pore volume exchanges, we were going to need to add air to the system. So we had injection points and extraction points, and we looked at combinations of those. We done tests on multiple points. Going back to the previous one, you can also test, and something that's very useful to do that not everybody does, is you can actually test the vapor probes themselves. So you can put as long as they're not too small, as long as the vacuum, you take into account the vacuum loss through the tubing, if you're using small tubing, and you account for that, you can actually get an airflow through them and an actual vacuum at the subsurface at the point, as long as you subtract out that drop in the pressure associated with the airflow going through a small tube. And again, you can get yourself a 3D determination of permeability. So you can see how even is that permeability around when you test the vapor probes as well as your SVE well. So going back to the big one, you can see that we have multiple wells, or injection, extraction, and you have multiple vapor points, and we monitor all of those during this this pilot test period. And because it was an extended pilot test, because it was a large site with a lot of contamination, we had to bring in, the other ones was short-term test, less than a day. We could discharge to the atmosphere. It was very little vapors, very low concentrations. Here we're dealing with pure product, and we had to have basically treatment controls to run that sort of system. I think that's where we stop with sort of the conceptual aspects of it before Dennis talks about the case studies. Dennis, did you want to entertain any questions, or did you want to just keep going based on timing?
I think we'll keep going right now, Mike. Only we don't have any questions yet in the chat, so just to remind the folks, if you have a question, to throw it in there. And what we'll do is towards the end, there were some questions associated with the registration that we had, and we'll make sure to get to those at the end here. But right now we're going to continue on, and then again, just enter the information to the chat that you want to ask, and we'll go from there. So I'm going to go next to the small case study that Mike kind of reviewed a little bit already. So this is a facility in Connecticut, had a history of metal manufacturing. So there was history of use of chlorinated halogenated solvents. As Mike had mentioned, relatively low site concentrations. If you look at this actual figure, one of our highest concentrations here is at this MW1 location, which is around 16 part per billion. So we're not talking about a very large source area by any means. One thing to note here is that this is a little bit misleading in that they don't have any sample locations up here, right? So this area here actually is the area where we found that we needed to treat based upon delineation. And that map, just so you know, was for PC, essentially we're dealing with here primarily is the contaminant concern. So some of the pre-design activities, first thing, any site, right, is delineation, right? Understanding where your source is, so you don't have to worry about implementing a remedy and then missing a third of it, because you didn't have proper delineation either in the horizontal or vertical directions. When we did that delineation, essentially, again, as Mike mentioned, low soil concentrations, sub part per million concentrations PC, suggested that soil vapor really was the primary source, especially in the Betos zone. In the vapor phase, when we tested those for PCE, range was about 100 part per million in the center area of the source area, and then we were about single digits along the outer edges. So again, pretty low concentrations relative to proper source areas where you have significant contamination. So as Mike mentioned, based on the low soil concentrations and the slightly elevated vapor concentrations, the overall site conceptual model was that we had essentially vapor deposition into groundwater, and that was causing those low part per billion concentrations in groundwater that were extending from the site source area. The pre-design activities then include some soil vapor well and vapor probe installation, and then some point permeability testing so that we could do a lot of pre-design activities that Mike had mentioned relative to some simple modeling and understanding kind of our pore volume exchanges and ground, or I'm sorry, our velocities. So the point permeability testing results here. The intrinsic permeability range from about 1 to 9 times 10 to the minus centimeters, 7 centimeters squared, which is about approximation of a clean medium sand. If you think in hydraulic terms, really you just kind of add 5 to this exponent here. So that's kind of equivalent to a 10 to the minus 2 centimeters per second hydraulic conductivity if you're used to seeing those. We then use that analytical model that Mike had mentioned, so not the 3D model. Again, this was kind of a relatively small site, lower budget, not as many regulatory submittals. So it was easy enough to figure out the pore volume exchanges using the simple analytical model. So really what we're looking to do here is sweep away these PCE concentrations in soil vapor. You know, there's no NAPL out here. We don't have to worry about very high soil concentrations. So your pore volume exchanges in this particular instance doesn't necessarily need to be as high as a site with, you know, more gross contamination. And we'll go through that in the next set of slides of the next case study for a much larger system. Based upon that analytical model, we had an extraction rate of about 13 to 17 SCFM, standard cubic feet per minute. In the middle area where we had those, you know, 100 ppmv concentrations, we designed for 1,000 pore volume exchanges per year. And then for the outer areas where we only had kind of single digits soil vapor concentrations, we were looking really more at 100 pore volume exchanges per year at this point. So this is the actual design. Essentially, we had 5 shallow and deep nested area or central areas here. So this is again the area where they had the 100 part per million per volume. So shallow and deep locations. We did a couple of things for the design. We were a little bit concerned about water entry into the subsurface, right? Essentially, if you get a lot of water in your vadozone relative to infiltration from precipitation, that can clog up your pore volumes. You could also generate quite a bit of water relative to when you're actually operating the system. You can entrain it in the vacuum, and basically it's brought up through the wells into your system, and then you have to handle that water, treat it and dispose of it properly. So we put a geotextile membrane over the area to prevent that water from seeping into the subsurface. We had another 5 locations out along the edge here, and those again are the ones we designed for the kind of 100 pore volume exchanges, the really much lower concentration areas. This was designed for seasonal operations, so we didn't have the need for heat tracing. The pipes were essentially run just along the ground. There's relatively open, sandy areas, so you know, easy access with no traffic. So relatively cheap and inexpensive to install at this particular location. We were able to operate for 2 seasons, and we did some optimization work. So a couple of things we did was pre-start soil vapor sampling. So the idea was to figure out, okay, so what are our startup concentrations at these kind of source area wells versus the outer areas which have less contaminated, and then we can optimize our flow rates in order to make sure that we maximize bang for our buck relative to the concentrations. We did some operation monitoring. So while the system is running, we're looking at flows and vacuums at all of these locations to understand how they're operating relative to the performance criteria we want. And then also we're monitoring to see what their concentrations are. And that was done every couple of months just to determine kind of which locations were, again, still producing vapors and optimizing the system. And then rebound monitoring. So when you're running the system, right, as Mike had mentioned, you're getting soil gas velocities and pore volume exchanges associated with that clean air that you're supposed to be bringing in from atmosphere. When you're doing this, essentially you're at disequilibrium, right? You have a certain amount of concentration that might be on soils or in these dead end pockets associated with the pore spaces. So what you can do is you can turn off the system and essentially let the air go stagnant, other than maybe some minor atmospheric pumping. When that air goes stagnant, you start to approach equilibrium conditions, and then you can basically sample these locations, get an understanding of you know, what those rebound concentrations might look like. This system operated for 2 seasons. The rebound soil vapor concentrations met shutdown criteria. One thing that is interesting about this project is we were very concerned, or we wanted to make sure that the concentrations that were remaining in the vadozone wouldn't negatively impact groundwater above the criteria for the site. So what we did was just a simple Henry's Law calculation, right? So Henry's Law is going to tell you, how much essentially is in water versus vapor. So we have these vapor concentrations that we collected at the wells, right? We took some analytical TO15 type air samples, soil vapor samples, sent them to the lab, got those results. You can use those results to basically predict how much would be in the vadose-owned pore water. When you do those calculations at the end of the system operation, we were below 0.5 part per billion. So reasonably successful project for the cost, without a doubt. Next project could be a little more significant. This is a site that's out in the Illinois area. And so here's a quick overview of the site. So this is in an urban industrial setting, right? This was actually incorporated in 1926. This town was specifically incorporated to be an industrial town. At the time, regulations were controlled more locally, so this town was set up essentially to have kind of looser regulations at the time so that they could operate more cost effectively. Has multiple industries in the area. Again, industry town, 249 people are currently living there today. The big thing to note here is that we have in this area right here a 2 million gallon benzene tank that was operated from about 1960 to 2000. And that tank had a cracked foundation. And as you can see, every villain deserves an evil mustache here. That's the area that we're talking about here relative to the operation or the pilot testing and design and operation of the SVE system. So I'm going to give you a quick cross section here. This is this, ground surfaces here. We have 3 layers. This layer was called our shallow zone. This area was our intermediate zone, deep zone. And then this area, as Mike mentioned, was our intermediate zone, which was a kind of a tight, silty clay associated with the geology in the area. The one thing I would note here is that groundwater was defined as regulatory as being about 15 feet. 15 feet. So the vadose zone, anything above 15 feet was considered vadose zone. The reality is that, I'm going to go back really quick, is that we have this small water body here called the Mississippi. And the Mississippi varies significantly relative to stage. So we found during operations that a lot of the times our groundwater was up at 8 feet, and in flood conditions, we would be just a couple of feet below ground surface in a lot of instances. So a lot more variable groundwater elevations than what was thought to be at the time. So what did we do with this site? So similar to the small one, we did some point permeability type work. That was upper and deep intervals. We were at 10 to the minus 8. And again, so you add 5 to that exponent. If you're thinking hydraulics, that's 10 to the minus 3, 5 times 10 to the minus 3. Intermediate clay was 1.3 times 10 to the minus 9. So again, that was pretty tight at that location. Dissimilar from the small site we discussed previously, our soil vapor field readings were maxed out the instrument pretty regularly. We were not, this was not an instance where, we were worried about just the soil vapor. There's significant soil contamination associated also on potential locations with some apple. Pilot testing. So Mike mentioned the pilot testing. One of the things that the client wanted to see and the regulatory agency wanted to see from the pilot testing was an actual reduction in mass. This is a source reduction application here. So the testing, was done from February to May back in 2010. It was conducted in the sandy fill and upper layer. We couldn't conduct it in the deeper layer, mostly because of groundwater issues. We were able to reduce the mass in that shallow layer by about 17,000 pounds. The actual soil vapor removed was 15,000 pounds, so the two agree reasonably well with each other. They did want us to test to see that we couldn't achieve any pore volume exchanges or soil gas velocities in that intermediate silty clay layer, and we couldn't. We basically proved that was going to be an unlikely solution for that location. And then from the actual pilot testing, soil permeabilities were around 4 times 10 to the minus 7 here. So one thing I want to note is point permeability is very analogous to a slug test in hydraulics. You're measuring kind of the soil, usually immediately adjacent to your vapor probe or SVE well that you're using. Right, when you're doing soil permeability as estimated during a pilot test, right, you're allowing yourself to take some induce a vacuum in the subsurface and measure your flow and vacuum at your extraction well, but now you're also measuring vacuums at a number of different locations nearby, right? So you get a much better average of what the overall permeability is. You get a much larger soil volume to do those measurements in. And here's the Air 3D modeling. So again, for the small one, we just did the analytical. For this particular location, we did the Air 3D modeling to get a look at what the interaction was between the SVE locations, right, which are located with the little arrows pointing inwards here. And we have some air injection locations here that represent the hours flowing out from it. We had an ROI of about 20-25 feet, so radius of influence. Our flow rate was on 25 to 30 SCFM. Right, and our overall estimated remedial time frame was 3 to 4 years. And I think someone had the question relative to our standard time frames. And usually we try to design systems, regular systems that have some soil contamination in the 3 to 4 year time frame if we can. There will be scenarios where you can do better than that. Obviously, the previous small case study, we were able to do that in a couple of kind of seasonal applications. And honestly, in that small case study, the second season probably wasn't even necessary. We probably could have done just the first season, but it was relatively cheap to operate. There are going to be instances where your time is maybe longer than that, and that depends upon site-specific factors, like if you're trying to treat lower permeability soils and there's diffusion and that kind of thing as far as rebound goes. I would note that the air injection locations here, were put in because, we're looking at the lower silty sand. So that's that third layer that's right above the groundwater table. This section here, we were very worried that discontinuous clay layer was going to impede fresh airflow from atmosphere down into this layer. So that was the reason why these were added. So they have that benefit. They have the secondary benefit of also increasing the number of pore volume exchanges you get down there just generally. So you can add them to systems if you want, right? If you feel it's beneficial, even if they don't have an issue with something impeding airflow from atmosphere. So system design specifications, after the pilot testing was completed, our SVE system was about a little over 2,000 SCFM. We added some air injection, which is 1,500 standard cubic feet per minute. 2 thermal oxidizers. So this is kind of important here. So anyone that's operated an SVE system in the past will know that usually what happens is that when you first operate the system, you're getting soil vapors from the subsurface that are in equilibrium. So generally they're much higher than they are during a year or two of operation down the road. And there's the question of always, how do you design your air treatment system relative to what concentrations you're going to see up front versus later on. So your upfront concentrations tend to be too rich, which means that you're unlikely or may not be able to operate all of your wells simultaneously as you had designed, and you'll have to wait for those vapor concentrations to attenuate so you don't get breakthrough or overwhelm your treatment system that you're using to attenuate those vapors. If you could also design for the lean side, if you like, right? So the lean side are very much lower concentrations, but then you basically extend the upfront portion, right? You're not able to treat nearly as much mass upfront. So there's always a trade-off here that engineering is trying to deal with. In this particular instance, we were, I'm not sure you use the term lucky, but there was other sites nearby that was owned by this manufacturer that had needed SVE also, and they're going to operate kind of simultaneously. So what we did is we had 2 thermal oxidizers built at the same time. We had a 2,000 SCFM one that was going to operate for our system over the entire course of operation, but then we brought in a 1,000 SCFM oxidizer in order to basically help with that upfront mass. And then after the first year, this 1,000 SCFM oxidizer was moved essentially to a new location after concentrations had declined. Pretty large area, 75 shallow, 82 deep SVE wells. I think, as I talked about here, the 2 thermal oxidizers, this 75 shallow wells, like we operate in the shallow interval first, we really only able to operate maybe 7 to 10 wells initially, right? That's how rich and how high the concentration was when we first turned on the system and got some of our first performance monitoring information back. we're taking benzene and we're introducing oxygen into the subsurface. So the question is always, is a possibility that you could elevate temperatures or something could happen where you actually could potentially start oxidizing benzene, start a small fire in the subsurface. So we actually did in this particular instance, because it was a sensitive site that actually did manufacture hazardous chemicals. So there were some sensitive processes nearby. We put in a thermal alarm, an interlock. So on our intake to the actual system, we were watching temperatures. That temperature got over a certain set point, we would shut the system down, and that would stop the SVs from running, and you would no longer be supplying oxygen to the subsurface. So kind of a safety interlock at that particular location. Our baseline mass removal rate. So when we first turned the system on, our shallow and deep baseline for each of the intervals was 160 and 115 pounds per hour. And to put it into kind of easier to understand terms, we were really looking at about 9.5 drums of benzene removed per day from the system when it first operated. And just a picture of it, you can see here's the equipment right here, and you'll see a little, it's kind of hard to see, but the little stack right there, and another even smaller stack right there. So this is that 2000 SCF oxidizer, and this is the smaller 1000. We have our main kind of trunk line here for our air injection and SV, and then each one of these are our SV and air injection locations. And actually this system does extend to the right of the page here. There's a small alleyway that this extended down along this major route here. So system performance. So this is operation over approximately 2.5 years. Here's our cumulative mass removes. This is additive, and this is our time frame when the system operated. Green means we operated the shallow. Red means we operated in, blue means we operated in the deep. And then the red means we operate in both, trying to optimize the system as much as possible. This is kind of a classic cumulative SV curve here. You get a much more of your mass removal up front in the first year or so, and then you start to attenuate, right, as the overall source area starts to decline in total mass and available mass. Our initial mass estimate for the site was approximately 390,000 pounds. And which is common with environmental sites. That estimate was probably a bit low. We ended up removing about 470,000 pounds of mass, actually. And I would note one other thing, this does not include aerobic biodegradation. So one of the benefits of soil vapor extraction with petroleum compounds, benzene, is that you're supplying oxygen to the subsurface, so you can stimulate basic biodegradation within the vadosone. We didn't really monitor for oxygen. If you actually monitor for oxygen, you can get an idea of how much is depleted and get a slight estimate or an estimate of how much is degraded. In this particular system, we didn't have that estimate. It wasn't part of the performance monitoring. So I'm almost done here, and then we can get to some questions if folks have them. So system was operated for about 2.5 years. And there was a bit of a question, and I'm kind of dating myself here a little bit. This is a commercial from the 70s and 80s, your chocolate's in my peanut butter, your peanut butter's in my chocolate. The question was, groundwater was at about 750 milligrams per liter, which is approximately half of solubility. And over the 2.5 years of operation, the system, the groundwater didn't really change. The regulators were kind of expecting in this particular instance that the concentrations go down. So there was a discussion relative to where that benzene was coming from. So is the benzene coming from leaching through the remaining impacts associated with the vadosone that the SVE was applied, or was it associated with concentrations that were below 15 feet in the saturated interval, and associated with historical smearing? So if you remember, we have this Mississippi River here that's located to the west of the site. The Mississippi River changes stage. So while at certain points our groundwater is at 7 feet below ground surface, there are times when it can be as low as 20 feet below. And we actually had a period of operation where groundwater thankfully was very low, so we were able to access pretty deep down to 15 feet. It actually caused navigation issues in the Mississippi at the particular time that this happened. So we actually got very good removal from that deep zone. But the question is historically you have this benzene, which acts as an LNAP, potentially historically sitting on top of the groundwater table. And as that groundwater fluctuation up and down between, let's say, 20 and 7 feet, you're kind of smearing that benzene to the pore volumes. So again, question is 750 milligrams per liter. Where is it coming from? Is it coming from infiltration precipitation, or is that basically a part of a source area that the SVE system couldn't treat? Like any good theory, we kind of took some additional samples, did some analysis, and kind of proved it out a bit. So as I mentioned, smear from groundwater table, right? Mass associated with soils. The saturated zone was really what the question was. So what we did is we took some samples from 0 to 15 feet, and these are the soil borings that we took the samples at, and we kind of estimated how much mass was associated with kind of a representative volume of each one of those soil borings. And as you can see here, our unsaturated zone, we ended up with a total mass of about 12,000 pounds in this particular location. Or if you look at the 0 to 15 feet, we're looking at about 1,000 pounds per foot of vadosome. If you took additional samples from the saturated, and as you can see here, we ended up with about 62,000 pounds, 63,000 pounds with a 12,500 pounds per foot associated with the system itself. So the question here is what's really likely causing or driving those 750 part per million concentrations of benzene and saturated was associated really with concentrations that were in the saturated zone themselves. Now, one of the interesting things here is if you think about it, we actually have kind of lower concentrations in our unsaturated zone than the saturated zone. And in that particular instance, what can actually happen is your variation in groundwater table, right, will cause a mass flux from that saturated zone actually into the vadosome. So you have this 750 milligrams per liter in groundwater. Groundwater rises to the Mississippi rising. You end up with this partitioning from groundwater into the cleaner soils associated with the vadosome, right? And then as it drops again, you end up re-equilibrating, and then you bring it up and it re-equilibrates onto the cleaner sand. So in this particular instance, it really didn't make much sense to operate the system much more, since if anything, the saturated zone was going to be partitioning benzene onto the vadosome, and we would end up just having to re-clean that over and over and over again. So the system has done the maximum it could do with its 470,000 pounds of mass removal at this point. So that is the end of my slides. And Mike, if you want to come back on here, and I'm going to just go to the chat here and see if we have any questions. I'm not seeing any questions in the chat at all, Mike. So let's go to the questions from the registration here really quick, and we have about 5 minutes, so that should be easy enough time. The first question was, what are some pitfalls as to why SVE is not successful? What are the options when the system reaches kind of end of life effectiveness, shutdown, pulse removal, that kind of thing? Do you want to go into that one?
Sure. Again, it is site specific. Based on our discussion today, I think the one big thing that I've seen over and over again is basically poor design of the system. And the system that is been installed and operated, if designed using the air exchanges, could have been a tremendously more efficient system. And so one answer is basically design. It's just simply the design process, and that they like the California site that I mentioned early on, where basically had been operating since 2002, and it still wasn't anywhere close to achieving its goal in 2018. That was a design issue. So that's one thing to be aware of. Obviously, there's other potentials. On the site that Dennis talked about, the larger site, when we were going through the process with the agencies, obviously we knew that there is some impacted soils that are tighter, and that there was not going to be effective clean air pore volume existed through the system, and they were going to then diffuse over long term. So the question is, do you continue to operate a system under those conditions as you did in the previous time frame necessary to get the majority of the contaminated mass out? And so what we had there was, we said, well, basically when it gets to that point where you're diffusion limited, you've got a few different options. Obviously, you got to look at risk. Is the risk of what's remaining a concern to the underlying groundwater or not? That's one. And then the second one, you can mathematically determine that. The second one basically is basically, well, if there is a risk associated with it, what's the most cost effective way? Is it to continue to operate your system? The answer is likely no. Is it to pulse your system? Or you could basically turn the system off for a month and then on for a few days and then back off for a month, a lot less operating cost, and it still gathers all the diffused vapors that come out from the system over that period of time. The other option basically is to go to something that's very cheap to operate, like just an injection only bioventing system. So in the case of petroleum, which is the site the dentist talked, we actually had a system, a process in place where we could turn the system to using the same infrastructure, but very cheap O&M costs. We could operate the system in a bioventing mode to destroy the petroleum as it came out of the system. As Dennis explained, in that particular case, we didn't need to because the impacts on the underlying groundwater, which was a different operational unit, OU unit, that basically was going to be treated in a different manner at this site. It's a very large facility with multiple OUs. And so therefore, basically, as Dennis pointed out, we couldn't do, there wasn't any benefit to continue to operate that system until the underlying OU was treated at a later stage with a different approach. So there's a lot of different things. So design, operational mode, these are the sort of things. Any of these systems that you design, regardless of the technology, you got to be monitoring it, but you got to be looking at the data. We've seen systems, whether it's pump and treat, whether it's solid vapor extraction, with any technologies that are in place and have been in place for decades, and basically data is collected, but it's really not reviewed. And so basically, or it's not reviewed with the context of, can you be more efficient? Should you be changing to a different approach or a different technology? So there's a lot of those things that are involved with looking at the data that you're collecting and making, common sense judgments as to, do you need to tweak something? Is there one recalcitrant hotspot that basically we done a thermally enhanced soil vapor extraction bioventing project, and we were able to turn 90% of it off within 18 months or 12 months actually. And there was a couple of hotspots, so we just needed to put some more focus on those couple of hotspots. And within 18 months, the total system was closed down. But again, that was making sure that you're looking at the data from the monitoring and making adjustments. And most sites require that, regardless of technology, to get to the endpoint in more cost effectively.
Yeah, the only thing I would add to the pulsing comment is the interesting thing about pulsing is that while it's more efficient, if you are looking to meet a certain remedial goal like a soil mass or a soil concentration, it actually tends to take longer than if you were to operate continuously. So, if time is an issue for you, it's definitely much more efficient and cheaper to operate in the pulse mode, right? But because you're not continuously sweeping away essentially those soil vapors, it will take some percentage longer potentially.
Correct.
Yeah. And I think that's all the questions we had there, Mike. So I think we're all set with the webinar here. I hope everyone found it useful. If you have any additional questions, please shoot either Mike or myself an email. We have our information listed right there on the slide, and we'll send out an email to all the registrants associated with where you can find a recording of this webinar, and then also we'll provide you a copy of the slide deck, so in case you want that. So great, I appreciate it and hope everyone has a good rest of the week. Thank you.
I know.